Hello everyone, welcome to session 12 of Principles of Aeronautical Engineering. So today we're going to talk about a little bit to flight mechanics. So let's start from this example. What you see here is a commercial aircraft flying from London in United Kingdom to Paris in France, and it's halfway and cruising at flight level of 330, meaning 30,000 feet. It's about 10 kilometers. So imagine that this airplane encounters a technical problem and all engines suddenly stop working, just like we gave an example of British Airways flight 009 back in 1982. So it's not a very hypothetical problem. It actually occurred at that time. So at that time, the aircraft went into the cloud of volcanic ash. So there might be a fuel running out. So it's not very hypothetical. So this British Airways flight 009 back in 1982 had this problem. It flew through a cloud of volcanic ash above Indonesia, and it resulted in the failure of all 4 engines. And for example, there is unfortunately no other option than to start gliding flight. And the question here is this: how far do you think that this aircraft can go gliding? So a typical commercial aircraft can glide more than 170 kilometers from this altitude of 30,000 feet or 10 kilometers. So in this specific scenario, the pilot could actually choose to glide either back to the London or go straight away and land in Paris safely. So this question is actually a typical question we encounter in the field of flight mechanics, and it shows one of the aircraft performance parameters, which is the glide. So how well one aircraft can glide actually. Some other key questions that we can address in flight mechanics is, for example, how far can an aircraft fly with a given amount of fuel, or how long can an aircraft fly time-wise with a given amount of fuel, or what's the maximum altitude that can be achieved, or how fast can an aircraft fly, or sometimes how slow can the aircraft fly. So it's obvious that the answer to these questions and similar questions depends on many things, which are, for example, aerodynamic shape of aircraft, the type of engines, and the aircraft weight, or some other parameters. So when you have the answer to these questions, you can start working on a very interesting topic, which is called the aircraft morphology. So aircraft morphology means that if you want a certain performance from an aircraft, then what is actually the optimum shape of that aircraft. Here you can see the difference between a civil aircraft and a military aircraft. So the morphology actually can answer to this question. Because of the certain performance, the shape of aircraft will change. Therefore, in flight mechanics, the performance of a complete aircraft is analyzed, and the question here is related to the motion of the aircraft. This means all information from different disciplines that we just studied together, like aerodynamics, the structure, or in other words, the weight of the aircraft, or the pilot itself, how does he or she operate the aircraft, the propulsion system, and also the atmosphere, so the ambient. All the information will be gathered and will be given to the flight mechanics. So since we are interested in calculating and finding answer to those questions, like how fast or how far or how slow or how high an aircraft is able to fly, so we should start by deriving the general equations of motion. So the first thing is that the Newton's first law, and it states that a body at rest remains at rest and a body in motion continues to move at constant velocity along a straight line unless there is an external force acted on this. So this law, as we mentioned, it only applies in an inertial frame of reference, or in other words, a frame of reference that does not accelerate. So imagine that you are inside a train and the windows are closed and you cannot look outside. And if from your own perspective or your own point of view, everything inside the train is at rest. So this is wild. If there would be a ball on the ground and the train would suddenly have to brake, the ball, as you see in here, start to move forward. But there is no external force acting on the ball. In fact, the ball just wants to continue moving forward, whereas the train is stopping. So similarly, if the train starts to turn, you can see that the ball can go left or right. Again, there is no external force that acts upon the ball, but because the train is experiencing an acceleration, the frame of reference is not an inertial frame of reference, and therefore the Newton's first law does not apply to this system. This is important to realize when we derive the equations of motion for an aircraft. So we should clearly define the difference between frame of references. So, a starting point, which seems more logical to us, is the Earth surface. So we can define a reference frame which is fixed to the Earth, as you see in here. So this reference frame is called the Earth axis system. Of course, we are interested in the motion of the aircraft relative to this frame, and there is this question if this frame of reference is an inertial frame of reference or not. Actually, we said that it is not, because if you're flying at a constant altitude above Earth's surface, you're actually moving in a circle, as you are seeing here. Therefore, an acceleration to the center of the circle or center of Earth is required in order to create this motion. So the frame of reference is accelerating, and it's not an inertial frame of reference for us. As a result, there appears to be a centrifugal force which works in the outward direction, perpendicular to the circular motion. And this is not a real force, but Actually, it's an apparent force, just like in the train example. So the question we have right now is that how large is this acceleration? So from high school physics, you know that this acceleration equals to v squared over r, this centrifugal acceleration. So and if you consider the cruise altitude of most common aircraft, which is about 10 kilometers above Earth, so the radius in the equation equals to the radius of Earth, which is 6,371 kilometers plus 10 kilometer of the height of the aircraft. And if you just consider a typical velocity of any commercial aircraft, which is about 0.8 Mach at this altitude, which is equal to 250 meters per second. If you calculate, you will end up with 0.0097 meters squared per second. This is the acceleration, and this is only 0.1% of the acceleration of Earth. So even though there is an acceleration, it is so small that we can neglect it and make this assumption of flat Earth. So flat Earth assumption means that the Earth is not rotating, is not actually round. So because of that, we can imagine the Earth as an inertial frame of reference. There is also another important effect, but right now I just mention it, and it's due to the rotation of the Earth, and we call it Coriolis effect. You can see this Coriolis effect in the below animation. So when a body is moving on a rotating frame of reference, there is always an acceleration because of this rotation. So it should be noted that the acceleration related to the fact that the Earth is rotating is very small, and also it can be neglected for most airplane motions. But as it will be important in when you consider high altitudes and high speed vehicles, when you're dealing with astronautics and orbital mechanics. So if we assume that the Earth is flat and is not rotating, we can safely state that the Earth fixed reference frame is inertial frame of reference. Now we can define some more useful reference frames. So the forces acting on the aircraft actually depend on the orientation and the motion of aircraft relative to the air. So for us, it would be useful to define the reference frames which is attached to the aircraft, not on the ground. So we can start by defining a reference frame with the same orientation as the original Earth fixed frame, but now we can attach it to the aircraft itself, and we call it the moving Earth axis system. So in here it is shown by X, E, and Z, E. So it's nothing but the Earth axis system, but attached to the aircraft. We call it moving Earth axis system. And here the nose of the aircraft is actually pointing in a different direction, as you can see. And you can also attach an axis system fixed to the aircraft body and call it body axis system. When the pilot is looking outside, he is looking along this x-axis of the body axis system, as you see in here with XB and ZB. He can directly observe the pitch attitude, this theta angle pitch attitude of the aircraft with respect to the horizon. So, summarizing, we have a reference frame from the point of view of the aircraft attitude, and we have two frames relative to the Earth. The Earth axis system, moving Earth axis system, and then the aircraft itself has the body axis system. But since we are interested in motion of the aircraft, there is one final element of interest, and that is the direction of the airspeed vector. So you should realize that an aircraft is not always following its nose. And in this picture at the left, you can see that the smoke of the aircraft is not moving in the opposite direction of the aircraft nose, but the nose actually has a slight angle with respect to the oncoming air. In most cases, the nose of the aircraft has a slight angle with respect to the airflow in order to generate the appropriate amount of lift, and unfortunately aerodynamic drag is there as well. So the angle of the airspeed vector with respect to the horizon, we call it the flight path angle, and the reference system attached to the airspeed vector is called the air path axis system. Now we have the reference frames defined, and we can start working on Newton's second law. If we can define all forces acting on the aircraft, then we can calculate the acceleration and thereby the motion of the aircraft. So let's identify which forces act on the aircraft. Of course, there is the gravitational force, W, you can see it. This is the weight, and this force acts on the aircraft and points to the center of the Earth. So it can be drawn along the z-axis of the moving Earth axis system. So this gravitational force is a function of a distance to the center of the Earth, and the variation is measurable but it's very small. So for our applications of aircraft flying below 80 kilometers height altitude, we can neglect this effect and assume that the gravitational acceleration is in fact constant. Now, if you draw the aerodynamic forces, the lift and drag, by definition, we have the lift force always perpendicular to the airspeed vector, and the drag is parallel to the airspeed vector v. Therefore, they are defined in the air path axis system, both of them. And the final force acting on the aircraft is the thrust force. And the thrust is coming from the propulsion system, and the direction of this force depends on how the propulsion system is positioned relative to the airframe. So if you draw in a general direction with some angle, you can see it has angle with respect to the airspeed vector, and you can call it as a thrust angle of attack, alpha t in here. So now you have defined all forces acting on the aircraft, and then you can have a look at the accelerations now. So what are the accelerations? Since we are looking at two-dimensional motion of the aircraft, the acceleration vector can be defined by two components. In principle, we are free to choose in which axis system we define the accelerations. But experience has shown us that defining them in air path axis system is the most convenient way. And if the aircraft has a forward acceleration along the x-axis of the air path axis system, it will change the magnitude of the airspeed vector. So the acceleration can be described as dv over dt. It is the change of velocity with time. So we are talking about the acceleration along v, along velocity, or along xa air path system. And normal to that, if there is a perpendicular acceleration, then the path of the airplane will be curved. And in fact, a perpendicular acceleration can be thought as a centripetal acceleration of a very big circle with radius r. You see it in here. And as you know, probably from high school physics, this centripetal acceleration is equal to v squared over r. Equation number 1. But this r is a bit meaningless in the context of our story, because we said that it is a very, very imaginary big circle. So it's the radius of this imaginary circle which you see at the right, and from this circle you know that the angular velocity multiplied by radius gives you the speed, equation 2. So omega times r gives you the linear speed v. And you can also observe from geometry of the circle that the angular velocity is in fact the same as the change of flight path angle with time. So this is given in equation 3. This omega is equal to rate of change of gamma, flight path angle. So d gamma dt. Therefore, you can observe that the velocity v can also be written as d gamma dt times r. So v squared over r, which is the centripetal acceleration, can be written equal to v times d gamma dt. So we basically replace one of the v's in the equation of equation 1. We can write it v times v over r, and v over r can be written as d gamma over dt. So the final results gives you the acceleration also equal to v times dt of flight path angle. So this is a nice form, because the equation of motion of the aircraft is purely defined by gamma and v, and these are only variables in the acceleration vector. So based on the forces and the accelerations, the point mass equation of motion can be written down, and it is most convenient to express them parallel and perpendicular to the airspeed vector, as we said. And these equations, when you write them, will form the basis for your aircraft performance calculations. So when you write those equations along v and perpendicular to v, you will come up with these two formulas, and I'll leave this as an exercise for you. So please work on this, and considering these two free body diagram and the kinetic diagram of aircraft in 2 dimensions, please derive the above equations and as your exercise for this session. So as you know, we wanted to answer some questions like this aircraft, how far this aircraft can go with some given amount of fuel, or how fast or how slow it can go, or what's the maximum altitude that the aircraft can achieve, or how steep one aircraft can climb. So basically you have these 2 equations with many unknowns. So that's typically something that cannot be solved, to 2 equations and too many unknowns. But if you look very closely to these 2 equations, there are actually 3 different types of variables you can find in these 2 equations. So the first one is the time. So you can call the time as independent variable. So during the flight, all the variables will change as a function of time, and you cannot influence it. The pilot cannot influence it. It will keep running no matter what you do. Time goes by. Another set of variables are 2 variables which we call state variables, which are gamma and the flight path angle. The gamma, which is flight path angle, and the velocity, which is the airspeed vector. So these variables actually express the state of the aircraft, the velocity of aircraft, and the gamma. And it indicates basically in which direction the aircraft is flying. So these are variables we would like to calculate if we try to answer questions, the questions we asked before. For example, how steep the aircraft can climb, and vice, etc. So finally, there are several other parameters like the thrust, the lift, aerodynamic force, the drag, the weight of the aircraft, angle of attack, for example, the thrust vector. So these are all a consequence of the pilot's control, or the state of the aircraft, or the atmospheric conditions. So these are other variables. Right now, if we can express these variables like the aerodynamic force as function of state variables, which are velocity and flight path angle, then the equation of motion become much simpler. So you're gonna have 2 equations and 2 unknowns. So you essentially remove all the variables and you can somehow solve these. So let's start with the aerodynamic forces and see if we can write or express these aerodynamic forces as a function of speed and gamma.